Okay, folks, welcome to Statistics HCM 5220. This is another video in a series. I just did one the other day based on normality, concepts of normality and errors in measurement or measurement error. And this one is designed to provide a little bit of background, quick background on uh, the modern scientific method, which was conceived back in the early 19th century and came sort of fully to bear late in the 19th century, and really was the reason for the vast technological development that we went through in the 20th century and actually up to today. Is it provides a way of testing fairly efficiently and fairly quickly different concepts, different ideas that we may have about um, some relationship between a couple of cause and effect, or in a couple of different variables that are related to each other, or, there's a lot of things that we can draw conclusions about that may turn out to be wrong, but the fact that we could draw a conclusion to a certain level meant that we could understand what was going on. Back during Newton's day, we understood gravity to be something that had to do with an attraction between two bodies, and the larger body had a greater attraction than the smaller body, and so the Earth had a greater attraction than the apple, and that explained how when you drop things they always fall to the ground, but it didn't really explain how things like the moon and things like that didn't absolutely fall to the ground, and so we needed a slightly better theory than just two bodies and the bigger one attracts the small one. And so we came to the conclusion that there must be more going on. And by the beginning of the 20th century, we had a groundbreaking paper by Einstein, basically his major contribution to science. A lot of very consequential contributions he made, but his major contribution was the understanding that the space-time continuum, that time was the fourth dimension, and that when a heavy mass is present in sort of the four-dimensional space-time, it warps the fabric of space-time, and his idea was that it was kind of like a plastic sheet that when you put a ball on it or a heavy ball on it, it'll warp, it'll sink down. And if you put a smaller ball on it somewhere close by, it won't warp as much. And there's a pretty good chance if you get too close, it's going to run downhill into the other. And so this thing that we call gravity, this attraction, was really sort of the process of something running downhill to a lower spot, and that would be the area that has a denser, more of a disrupted space-time fabric, because it's denser and heavier. And a lot of things came out of that, and black holes and all that sort of stuff. But what it was, it allowed us to see why the moon stayed where it was, and why it went around the Earth and couldn't break free from the Earth, and all those things, and in a way that Newton's explanation didn't. Well, now we know that neither one of those are exactly true, because we don't take into account the effects of the quantum universe and of quantum mechanics. And in quantum mechanics, and I wouldn't even try to put a common sense analogy to that, but quantum mechanics basically says that all things come in small quanta, and for different things, it's different quanta. There's photons for visible light. There's gravitons for gravity. There's different things that you can break down into smaller and smaller packets of information, and at some point those packets of information become just energy. And so the Earth is a constant battle between matter and antimatter and energy and mass and all those sorts of things. And so it makes your head hurt to think about it, but it also meant that this modern scientific method allowed us to add on to ideas that had merit, but maybe we didn't know enough, or we couldn't measure it, or we just didn't have the science to be able to understand it in a different way. And so in the early 19th century and into the 20th century, the modern scientific method became a boon. And I want to show you a quick little example here, a little graphic example, simple little graphic that may help kind of explain how we fit some of these concepts together, this idea of modern scientific method with earlier concepts of measurement error, normality, and randomness and all that. So I'm going to share up my visualizer pad over here. Find it. Okay. Now this is just a very simple, quick little rudimentary example, and I'm kind of saying, okay, we've got a population here that we're dealing with, and the size of that population is somewhat less than zero. I mean, excuse me, somewhat less than infinity. 30 or 7 trillion or whatever, but it's less than infinity. And let's say it's a measurement of people's IQs, and the mean IQ, that's what this big M means, the mu, the mean IQ of this population is 110. And so because it's a random piece of data and it's a large population, all we know that this distribution up here will be normally distributed, and it'll have a normal distribution, and it's kind of spread out because there's a big pile of numbers there, and in the center of that is the mean, and above that 50% of the cases lie, and below that 50% of the cases lie. And so it, because it's a perfect it's a perfect normal distribution, we know that. Now if we take advantage of the properties of randomness and say we go and we select 25 individuals and we drop them over here in what we'll call group A, and we take another random 25 individuals and we drop them in over there in group B. Because of what we know about normal distributions, because of what we know about randomness, and because of what we know about the central limits theorem, we know that the most likely average IQ for group A is going to be 110, because that's the largest occurring score in the population. The mean is always, in a random population, the highest occurring score. And we also know, because once again, group B is a random group, that it also has an IQ of, we would estimate at 110. Now these are estimates, we're not measuring or anything, we're just saying if we pick random samples, they should be representative of the population. In this case, they should have an average IQ of 110. And making that assumption about normality and about randomness, we can assume that these two groups are equal to begin with. A and B are equal to begin with. And this is the basic first important concept that we grabbed into in terms of the modern scientific method, that if you picked random groups, you could assume, you didn't have to measure them, you could assume that those random groups had relatively identical properties. And as the N got larger and larger and larger, that assumption became more solid. And so the bigger your groups, the more you could be sure that the two groups were equal if you drew them randomly from the same population. Now, the second part of the modern scientific method is that then we would do something different to the two groups. And so we would have one group over here, group A, and X's we refer to as treatment variables, and group B. And let's say that group A gets some activity, some special organized activity designed to foster critical thinking and more advanced thinking, and that this extra activity we define as the treatment, and the lack of that activity we define as the control. And so we have a treatment group and a control group, and they were the same to begin with, and now we're going to do this for some period of time, and let's say we do this for 6 months. And so at the end of 6 months we come back and we remeasure folks in group A, or we actually measure folks in group A because we hadn't done that yet. And so this becomes the second iteration of A. And we find that now we still have 25, and we assume that after we measure their IQ the second time, we realize that has gone up to 115 on average. And we look at group B, and so this is actually the second time. And so still have 25, and the IQ, average IQ for group B, second time, is 108. And so the control group had an average IQ of 108 after 6 months. The experimental group had an average of 115 after 6 months. And so we know there is a difference here of 7 points. There's a difference of 7 points. What we don't know is whether that is a meaningful difference or not, or whether it's just a random difference. That language may sound familiar, meaningful and random. And we're going to skip back over to another share for just a second, which was this notion of measurement error. Now, measurement error is composed of two components, random and systemic. We know they're there, we just don't know in what proportion and how large they are overall. But we know they're there. And if we could know what the likelihood was of a systematic error, then we could make some meaningful statement about whether 7 was a significant difference or not. And so if we begin to look at nature of error, first thing we notice is that the nature of error is random. Nature of error is random. And it is clustered around the mean, the measured mean of the variable. And we also know that systematic error is also normal. That's this red curve here. But it does affect the average. In this case, it's below the average of the distribution without any systematic error, the distribution with just random error. And so the blue distribution is just random error. That's all the error that's in there. So that error is clustered around the mean of the variable. the distribution of the same variable with systematic error is not clustered around the same mean. In fact, it's clustered lower. And so the difference between these two means can tell us something about how much of that error is something we need to worry about. But we have to have some way of estimating what the random error would be. There has to be some way of estimating what the random error would be. And so we try, the statistics is all about trying to come up with that estimate of random error and the things that we know about it. And it's called an unbiased estimate. The things that we know about it for sure is that we know that it is distributed in a normal manner. That's not a good normal, it never meets, but it is distributed in a normal manner. And the other thing we know is that this unbiased estimator has the same mean as the population. And so we know the mean and we know the distribution. But what we don't know is how to align proportions and percentages on this distribution. Let's go back over that again. We know that it's random, unbiased. This unbiased estimate is random. So it's normal, and we know that its mean is at the mean of the population. Okay, there it is. I finally shared it up. Finally went. We know that it's random, therefore normal, and we know that its mean is the same as the population mean. So we know a couple of things, but we don't know enough yet to be able to understand whether 7 is truly a difference. Is this a real difference or not? And that becomes the meaningful difference. What is how much of an estimate can we put on whether 7 is a meaningful difference, what we would call a significant difference, or not? And right now, we don't know enough. We need another piece to the formula. We need one more piece to the formula. And so we'll talk about that in the next video, what that next piece is and what it means to us when we plug that piece of the puzzle in. Also, between now and I guess next Wednesday, I'll have up a video or two of JASP and working with JASP. And I don't know, we'll just see how many videos I get up there because it's probably going to be 2 or 3. So this is the end of the video related to the modern scientific method. And it leaves in a quandary and a question. And so we have to figure out, how do we know when a real difference is a difference?